Welcome, amazing students of Ishik Boys High School, and a special hello to everyone in Mr. Jager's class. Welcome to For the Love of Physics podcast. We are Mr. Jager's assistant. Today, we're doing a deep dive into something you see, well, probably every day, especially when it's sunny. We're tackling the polarization of light waves.
Oh yeah, it's super relevant. Think about polarized sunglasses, right? How they cut down glare.
Exactly. That annoying glare off a lake or even a wet road.
It's not just making things darker. There's some really cool physics going on there, and that's what we're going to unpack today.
Okay, so let's start with the basics. Light from, say, the sun or just a regular light bulb in your room. What kind of light is that usually?
A good starting point. Yeah, most of the time that's what we call unpolarized light. Imagine the light wave is traveling towards you, right? The electric field part of that wave is vibrating, wiggling back and forth.
Okay.
An unpolarized light, it's wiggling in all possible directions, perpendicular to its path. Up, down, left, right, diagonally. It's like total chaos.
Like shaking a rope completely randomly, every which way.
Exactly like that. It's a jumble of vibrations.
Yeah.
That's your standard unpolarized light.
So it's all messy, but can we simplify that picture a bit? Is there a way to think about it that's easier?
Yeah, we can actually. Even with all that randomness, mathematically, you can think of any random aberration as being made up of basically a vertical part and a horizontal part.
Ah, okay, like components.
Right, just vertical wiggles and horizontal wiggles added together can represent all that chaos. It helps us understand what happens next.
Okay, so that leads us to organizing it. What happens when we get those vibrations to line up?
That's where we get linear polarization.
Yeah.
So now, instead of vibrating every which way, all the electric fields are vibrating parallel to each other, lined up.
So back to the rope analogy.
Yeah, instead of shaking it randomly, now you're only shaking it strictly up and down, or only side to side, just one direction. That's linearly polarized.
Okay, got it. Unpolarized is random, linear is lined up. So how do we actually make light linearly polarized? How does that happen?
Right, how do we filter out the chaos? One really common way is polarization by transmission. There are certain materials, some crystals, special plastic films. Their molecules are arranged in a very specific way, like tiny, tiny rows.
And these act like a filter.
Exactly. When unpolarized light hits this material, it only lets light waves through if their vibrations are lined up with the slots in the material, so to speak.
And that direction, the direction it lets light through, that has a name, right?
Yep, that's called the transmission axis of the material. Think of it like the direction of the slats in a picket fence. If the light wave is vibrating parallel to those slats, it slips right through.
But if it's vibrating the wrong way, like
Right.
perpendicular.
It gets blocked completely. It just can't make it through those tiny molecular slats if it's vibrating at a 90-degree angle to them.
Okay, this sounds like something you could actually see happen, like with those polarizing films.
Oh, absolutely. It's a
Right.
classic demo. If you take
Yeah.
two pieces of this polarizing film and you hold them so their transmission axes are lined up parallel, light goes through both. You can see through them fine, like looking through two fences with vertical slats lined up.
Okay, makes sense.
But then, if you rotate one of those films, say 90 degrees, so now one has a vertical axis and the other has a horizontal axis,
What happens?
boom, almost complete darkness. No light gets through. Because the light that gets through the first filter, say vertically polarized, is vibrating the wrong way to get through the second horizontal filter.
Wow. So one fence has vertical slats, the other has horizontal. Nothing gets through both.
Precisely. It's a really strong visual for how this filtering works.
So this isn't just cool to watch. It means we can actually figure out if light is polarized and which way it's vibrating.
You got it.
Yeah.
It's exactly how we detect polarization. If you have a beam of light and you're not sure if it's polarized, just take a polarizing filter, like pop a lens out of some polarized sunglasses,
Okay.
and rotate it in the beam. If the brightness changes as you rotate it, getting brighter and dimmer,
Then the light must be polarized.
right, it'll be brightest when the filter's transmission axis lines up with the light's vibration direction, and dimmest or even black when they're perpendicular. You can literally see the polarization.
That's really cool. So, okay, filtering is one way. You mentioned glare earlier. Does light get polarized just by bouncing off things?
It sure does. That's the second major way. Polarization by reflection. When unpolarized light hits a surface, especially something like water or glass, or even the road,
Yeah.
the reflected light can become partially or sometimes almost completely polarized.
And that's related to that awful glare we talked about, the kind that makes it hard to see.
Exactly. That blinding glare you get off a wet road or the surface of a lake, that is reflected light. And here's the key thing.
Yeah.
It's often strongly horizontally polarized. The electric fields are vibrating mostly parallel to the surface they bounced off of.
So parallel to the ground or the
Yeah.
water surface.
Yep. All those reflected light waves are vibrating side to side, more or less. And because they're lined up, they hit your eyes as a really intense, annoying glare.
Ah, okay. So that's why polarized sunglasses work so well against glare. They must be designed to block that specific type of light.
Bingo. Your polarized sunglasses are made with their transmission axis set vertically.
Vertically. Okay, so the glare is horizontal.
And the sunglasses are like a vertical fence. They let the useful vertically vibrating light through so you can see, but they block almost all of that intense horizontally vibrating glare.
It's like they specifically target and eliminate the annoying part of the reflection.
Pretty much. It's not just dimming everything, it's selectively removing that horizontal glare component. That's why things look clearer, not just darker.
That is so clever. Okay, so transmission, reflection. Are there other ways? I think I remember reading about crystals doing something weird with light.
Ah, yes, good point. There's also polarization by multiple refraction, or sometimes called birefringence. This involves certain types of crystals. There's a cool historical story here. Back in 1808, a scientist named Malus was looking at sunlight reflecting off a window through a crystal, a calcite crystal.
What did he see?
He saw two images of the reflection. And even weirder, as he rotated the crystal, one image got dimmer while the other got brighter.
Two images from one reflection. That is weird.
Totally. It baffled people, but it was a huge clue that light had this directional property, this polarization. It wasn't just a simple ray.
So that discovery led to ways to actually use crystals to create polarized light deliberately.
It did. It led to things like the Nichols prism, developed a bit later. It's made from calcite, cut in a very specific way. You don't need to worry about the exact geometry, but the basic idea is pretty neat.
How does it work, roughly?
Well, when unpolarized light enters this specially cut crystal, the crystal's structure essentially splits the light into two separate beams.
Based on polarization.
Exactly. The crystal structure interacts differently with light vibrating in different directions.
Yeah.
So one beam, maybe the vertically polarized light, goes straight through. That's your transmitted polarized ray. Pure, linearly polarized light.
And the other beam, the horizontal part.
It gets bent off course, reflected internally, and emerges somewhere else or gets absorbed. That's the reflected polarized ray. So the prism acts like a very precise sorter, separating the unpolarized light into two distinct polarized beams.
Wow, so it physically separates the different polarizations. That's amazing.
It was incredibly important for experiments, giving scientists a reliable source of purely polarized light to study.
What a journey, from random vibrations to perfectly sorted beams. Okay, let's recap quickly. We talked about unpolarized light vibrations in all directions and linearly polarized light vibrations lined up in just one direction.
Yep, and we saw how light can get polarized through transmission, using filters with a specific transmission axis.
Like in polarizing films or those sunglasses.
Right, and also through reflection, which is why glare is horizontally polarized and why those vertically oriented sunglasses work so well.
And finally, that cool crystal method, multiple refraction, like in a Nichols prism, that actually splits light into two polarized beams.
You got it. Those are the main ways polarization happens and how we use it.
Okay, here's something for you students to think about.
Next time you look at your phone screen, or maybe an LCD TV screen, while you're wearing polarized sunglasses, try tilting your head slowly side to side.
Well, yeah, good one.
What happens to how bright the screen looks? And based on what we talked about, why do you think that happens? Give us some thought.
Stay in contact with your physics teacher, stay creative,